December 9, 1941. Pearl Harbor. The battleships have stopped burning, but across the Pacific theater a different crisis unfolds. At Wake Island, canvas tents collapse under tropical downpours. In the Philippines, ammunition depots flood as fabric shelters disintegrate after 3 weeks of monsoon rain. The pneumonia ward fills faster than the casualty ward. By dawn, Brigadier General Eugene Raybould stands before a conference table in Washington, staring at weather maps and construction timelines that don't add up. The math is brutal. 2 million men need shelter across hundreds of islands. Conventional barracks take 6 weeks to build and require skilled carpenters who don't exist on coral atolls. Canvas tents cost $12 but last 1 month before rotting apart. The War Department needs structures that can be manufactured in Pennsylvania, survive typhoons and Japanese bombs, and assemble in 1 day by exhausted Marines who've never held a wrench. And they need the first 10,000 units ready in 6 months. In that moment, as Raybould circled the impossible specifications, American engineering faced a problem that would define modern disaster response for the next 80 years. Before we dive deeper into this incredible story of innovation under impossible pressure, I want to take a moment to thank this amazing global community. It's absolutely mind-blowing that right now, someone in Australia might be watching this during their morning coffee while someone in Norway watches before bed, and someone in Brazil tunes in during lunch. Where are you watching from? Drop your location in the comments, and if you're enjoying these deep dives into the engineering and logistics that shaped history, hit that like button and subscribe. These stories of innovation under pressure deserve to be remembered. Now let's get back to 1941, when American engineers had 60 days to design a building that didn't yet exist. The British provided the starting point, though they didn't know it yet. Since 1916, their forces had used Nissen huts, semi-circular steel shelters invented by Canadian engineer Peter Nissen during World War I. These corrugated iron half-cylinders housed 30 soldiers and required no skilled labor to erect. They'd survive sandstorms in North Africa and winter gales in France. But the Nissen design carried fatal flaws for Pacific deployment. Each hut weighed 3 tons disassembled. The ventilation system worked for Libyan deserts, but transformed Philippine humidity into a steam cooker. Most critically, every unit required custom foundation work, concrete poured or wooden platforms built, which meant finding carpenters who simply didn't exist on remote islands. In February 1942, detailed Nissen blueprints arrived at the Navy's Bureau of Yards and Docks in Rhode Island. Commander John Philip Drosfeld studied the specifications and immediately saw both genius and catastrophe. The genius was the arch shape, which naturally deflected wind and shed water without complex engineering. The catastrophe was everything else. The internal wooden frame would become termite food within months. The small windows designed for Scottish weather would create ovens in 98-degree Guadalcanal heat. The weight made shipping prohibitively expensive. But there was another voice in this conversation, though he wasn't in the room. Buckminster Fuller had been preaching prefabricated housing since the 1920s, and most architects dismissed him as a crank. His Dymaxion house concept, factory-built, lightweight, assembled on-site, sounded like science fiction. But in 1942, Fuller's ideas about mass-producing housing like automobiles suddenly sounded less crazy when your country needed to build a city's worth of shelter every month. His core insight proved invaluable, even though the military never directly consulted him. Treat buildings like manufactured products, not construction projects. The Navy consolidated this thinking at Quonset Point, Rhode Island, a freshly commissioned air station on Narragansett Bay. The location wasn't random. Rhode Island had deep sheet metal expertise from its jewelry and silverware industries, plus proximity to Pennsylvania steel mills and shipyards that understood marine-grade corrosion resistance. In March 1942, an unusual team assembled, structural engineers from Strand Steel Corporation who'd been building prefab farm buildings, architects from George A. Fuller Construction Company, who specialized in rapid assembly, Navy officers who'd actually served in the Pacific and knew what typhoon-proof really meant versus what it meant on paper. Otto Brandenberger led the team, bringing farm building experience that proved exactly right for this problem. His Strand steel barns used self-supporting arched panels with no internal frame, which meant no wood for termites and no complex joints to fail during storms. His radical proposal violated conventional architectural wisdom. Eliminate the Nissen hut's wooden skeleton entirely and make the corrugated steel skin carry all loads. In 1942, steel was for bridges and skyscrapers, not self-supporting buildings, but Brandenburger's barns had survived Midwest tornadoes without internal framing. He was willing to bet the same principle scaled up. April 15, 1942. Brandenburger walked into a Quonset Point warehouse with 30 engineers and a deadline that would be laughable if the war situation weren't desperate. 60 days to design, prototype, test, and approve a completely new building system. The team worked in shifts around the clock, sleeping on cots against warehouse walls, subsisting on Navy mess hall coffee and pressure that either produces brilliance or complete collapse. The first radical decision happened on day 3. Traditional architectural drawings took weeks to produce. The team didn't have weeks. Instead, they built in real time. Sketch a detail in the morning, have the metalworking shop fabricate it by afternoon, test it overnight, revise by dawn. This iterative prototyping was revolutionary in 1942, when buildings were designed completely on paper before cutting a single piece. The warehouse floor became a laboratory scattered with failed joint experiments, bent test panels, and increasingly refined component versions. The dimensions came from brutal practicality. 16 feet wide, the maximum that fit on standard rail cars without special permits. 20 feet long per section, short enough that 4 men could lift a panel but long enough to create usable space. 48 feet total length when assembled, housing 36 men with bunks or converting to offices, medical stations, supply storage. This size hit a structural sweet spot. Smaller wasted shipping capacity. Larger made panels too heavy for field assembly, or required internal supports that reintroduced all the problems they were eliminating. The arch radius calculation consumed 2 weeks of their 60-day deadline. Too flat and wind forces could peel the structure like a sardine can. Too steep and you wasted interior headroom and created difficult end wall geometry. Brandenburger's team settled on an 8-foot radius, a perfect semicircle providing 7-foot headroom at the sides, and creating what structural engineers call a self-bracing arch. The corrugated steel naturally wanted to hold this curve, meaning panels could be thinner and lighter than flat sheets would require for the same strength. They ran load calculations showing the design could theoretically handle snow loads up to 40 pounds per square foot and wind speeds exceeding 100 miles per hour. But theoretical calculations and Pacific typhoons were different animals. By day 40, they had something that looked like it might work. A Frankenstein's monster of riveted panels, experimental joints, and borrowed hardware. The first complete prototype went up on May 25, 1942, assembled by 6 sailors given 4 hours of instruction and basic hand tools. Assembly time was 14 hours. Encouraging, but not good enough. The Navy wanted single-day construction because marine landing schedules didn't allow multi-day building projects. The team identified the bottleneck immediately: the floor system. They'd been trying to include wooden floors, but it was the slowest part to assemble, and the first thing to rot in tropical conditions anyway. The solution was elegant in its simplicity. Eliminate the floor entirely from the basic design. The hut sat directly on whatever surface existed: coral, sand, dirt, or gravel. For applications requiring finished floors, those could be added later as separate projects, but the basic shelter achieved weather protection without them. This single decision cut assembly time to 8 hours and reduced shipping weight by 1,200 pounds per unit. On June 10, 1942, the final prototype stood complete. 96 corrugated steel panels, each weighing less than 50 pounds, bolting together to create 720 square feet of enclosed space. Total materials cost $1,394. Total weight 9,000 pounds. The real test began when Navy structural engineers arrived with wind load tables, typhoon data from meteorological stations across the Pacific, and healthy skepticism that this corrugated tunnel could survive what nature threw at tropical islands. The numbers they worked with weren't theoretical. Typhoon Gloria hit Guam in November 1940, with sustained winds of 140 miles per hour and gusts reaching 180. The 1935 Labor Day hurricane killed 400 people in the Florida Keys, with winds so powerful they sandblasted paint off buildings and drove wooden planks through palm trees like spears. Brandenburger's team started with fundamental physics of why the arch worked. When wind hit a flat wall, it created maximum force pushing directly against the surface, but a curved surface deflected wind upward and around, reducing pressure dramatically. Think of water flowing around a river stone versus slamming into a dam wall. The semicircular Quonset profile meant hurricane-force winds slid over the structure, rather than trying to punch through it. The corrugations added a second layer of brilliance. Those ridges running lengthwise created structural rigidity, the way folding paper makes it stronger than leaving it flat. Each corrugation acted like a tiny I-beam, resisting bending forces that would crumple smooth sheet metal. In a conventional rectangular building, roofs pushed down on walls pushed down on foundations, and everything depended on vertical load paths staying intact. Storm winds could literally lift roofs off because they were separate elements sitting on top of walls. The Quonset arch changed this completely. It was a single continuous curve where every panel shared load with its neighbors. Engineers called this a compression ring, the same principle that kept stone bridges standing for centuries without mortar. Each Quonset panel bolted to adjacent panels with 3/4-inch steel bolts spaced every 6 inches, creating essentially a 48-foot-long steel cable wrapped in an arch shape. But theoretical strength meant nothing without testing. The Navy built a full-scale Quonset at Davisville, Rhode Island, and instrumented it with strain gauges, pressure sensors, and deflection meters. Then they waited for the first major nor'easter. On March 3, 1943, a storm hit with 75-mile-per-hour winds and heavy snow loading. The instruments recorded the structure flexing less than 2 inches at the crown, then returning to original shape when wind subsided. Panel joints held. Nothing leaked. The structure behaved exactly as calculations predicted, which was both thrilling and terrifying because it meant they were about to bet thousands of lives on this design. June 1942. The War Production Board approved Quonset hut manufacturing, and American industrial capacity operated at absolute peak. The Navy contracted with 10 major steel fabricators across the Midwest and Northeast. Companies making grain silos and water tanks 6 months ago retooled for military shelter production. Strand Steel converted its entire Penrose facility outside Philadelphia to exclusive Quonset production. George A. Fuller Construction took over a former auto parts plant in Chicago. Great Lakes Steel dedicated 2 rolling mills to nothing but corrugated panel production. By August, these factories collectively produced 1,500 complete huts per week, and the number kept climbing. The manufacturing process borrowed heavily from automotive assembly line logic. Massive steel coils arrived by rail. Each coil contained enough steel for 30 panels. Rolling machines corrugated flat steel, creating structural ridges at precisely 2.67 inches on center. The corrugating process work-hardened the steel, making it stronger than the flat sheet that went in. Next, panels went through galvanizing tanks, dipped in molten zinc at 850 degrees Fahrenheit. This zinc coating wasn't paint. It was a metallurgical bond that sacrificed itself to corrosion before underlying steel could rust. In Pacific saltwater air, this galvanizing meant the difference between 5-year lifespan and 50-year lifespan. The process cost an extra $112 per hut but proved non-negotiable, after field reports showed ungalvanized steel corroding through in 8 months. Each complete hut kit got packaged with obsessive attention to shipping logistics. The 96 corrugated panels nested inside each other like stacked bowls, reducing package height from 8 feet to just 14 inches. End walls packed flat between steel panels. All fasteners and hardware boxed in a single crate with illustrated assembly instructions designed for men who might not read English fluently. The entire kit loaded onto one standard 40-foot flatbed railcar. Guadalcanal, August 1942. The first combat-deployed Quonset huts arrived on a beach where temperature hovered at 95 degrees with 90% humidity, and Japanese bombers made daily visits. Marine engineers unloaded flat-packed steel panels under sporadic artillery fire and started bolting them together in a coconut grove, still showing scorch marks from the previous week's shelling. Within 12 hours, Henderson Field had 10 new structures housing maintenance crews for battered F-4F Wildcats. The real test came 3 days later when a Japanese bombing run scored a near miss. A 500-pound bomb detonated 40 yards from a hut full of aviation mechanics. The blast wave flattened surrounding palm trees and shredded canvas tents like tissue paper, but the Quonset flexed. Dirt and shrapnel rattled off corrugated steel. When smoke cleared, the structure stood intact with every man inside shaken but alive. Iwo Jima, February 1945. The volcanic island offered a different hell. Black sand that blew into every crevice, no topsoil for grounding stakes, and constant threat of artillery from Mount Suribachi. Seabees arrived on D-Day +2. and started assembling Quonset huts under fire, literally bolting panels together while mortar rounds impacted 200 yards away. The volcanic sand proved impossible for traditional stake anchoring. Crews improvised by filling empty oil drums with sand, connecting drums to hut bases with cables. When a Pacific typhoon hit in March with 110-mile-per-hour winds, those improvised anchors held while wooden structures across the island disintegrated. The base commander's report back to Pearl Harbor was succinct. Quonset huts survived. Everything else gone. By mid-1944, monthly production hit 8,000 units. The logistics network moved so efficiently that huts ordered in Pennsylvania reached New Guinea within 40 days, including ocean crossing and trans-Pacific transport. Each Quonset provided 36 men with weatherproof shelter for $1,394 in materials and approximately 60 man-hours of assembly labor. Compare this to conventional barracks: $12,000 in materials, 400 man-hours of skilled carpentry, 6 weeks construction time. The Quonset delivered shelter at 1/10 the cost in 1/20th the time. By war's end, the United States military had deployed over 170,000 units to every combat theater. That's housing capacity for nearly 6 million personnel built in less than 2 years. May 8, 1945, victory in Europe. August 15, 1945, victory over Japan. Suddenly, the military owned roughly 170,000 Quonset huts scattered across 6 continents and had no idea what to do with them. The original plan assumed these were temporary expedients that would be scrapped once permanent facilities could be built. But something unexpected happened. Nobody wanted to get rid of them. Veterans returning home discovered a housing shortage so severe that families lived in converted chicken coops and shared apartments with 3 other families. The construction industry, starved of materials and labor during 4 years of war, couldn't build fast enough. Into this crisis stepped the Quonset hut, available for civilian purchase at liquidation prices, $1,000 to $2,500 for a complete structure that would cost $8,000 to build conventionally, if you could even find contractors. Roger Young Village in Los Angeles housed 750 families in converted military huts. Vetville developments appeared near universities where the GI Bill flooded campuses with students needing immediate housing. Families added wooden facades to curved ends, making structures look less like military surplus and more like quirky cottages. Interior walls divided open space into bedrooms, living areas, kitchens. Some owners buried entire structures halfway into the ground for earth-sheltered insulation, or connected multiple huts end to end, creating sprawling compounds. Churches discovered Quonset huts solved providing worship space for exploding suburban populations without decade-long capital campaigns. First Presbyterian Church of Levittown, Pennsylvania, held services in a Quonset hut from 1952 until 1967. The acoustics were terrible, aesthetics underwhelming, but people could gather for worship next month instead of next decade. Some temporary church huts remained in service for 30 years. Modern disaster zones tell you everything about why Quonset DNA keeps reappearing in 21st century emergency response. When the 2010 Haiti earthquake destroyed Port-au-Prince, relief organizations faced the same equation American planners confronted in 1942. Immediate shelter for hundreds of thousands, no existing infrastructure, no time for conventional construction. The solution that emerged borrowed directly from Quonset principles: arched steel frames, corrugated metal panels, prefabricated components shipping flat and assembling quickly. The United Nations High Commissioner for Refugees currently uses shelter systems called RHUs, refugee housing units, that are essentially Quonset huts with 80 years of material science improvements. Instead of corrugated steel, they use insulated composite panels. Instead of bolt-together assembly, snap-fit connections. But the core concept remains identical. Curved profile for structural efficiency, self-supporting arch eliminating internal framing, flat-pack shipping allowing massive quantities to reach remote locations, assembly by unskilled labor with minimal tools. A 2-person crew can erect a modern RHU in 4 hours, almost exactly matching 1942 Quonset specifications. Perhaps the ultimate validation comes from space exploration. NASA and private space companies designing Mars habitats keep arriving at Quonset-like solutions. Proposed Martian shelters feature arched profiles to resist severe dust storms, prefabricated components shipping on spacecraft, self-supporting structures not requiring extensive foundation work in Martian regolith. The constraints of interplanetary construction, extreme environments, minimal tools, unskilled assembly, maximum strength from minimum materials, mirror Pacific theater challenges of 1942, so precisely that engineers independently rediscover the same solutions. When humans finally build permanent shelters on another planet, there's a reasonable chance those structures will owe their design heritage to 30 engineers working in a Rhode Island warehouse during the darkest days of World War II, solving an impossible problem with corrugated steel and brilliant simplicity. They didn't just design a building. They designed a principle that survives because the physics of curves and compression rings and self-supporting arches don't change with time. They created shelter that worked because they understood something fundamental about scarcity, logistics, and human ingenuity under pressure, and in doing so, they proved that sometimes the most elegant solutions come not from unlimited resources, but from impossible constraints that force you to think differently.